Measurement of suction for fly ashes. Abstract fly ash has found wide application in agriculture, landfill liners and covers, etc., where its water retention relationship becomes important. Water retention relationship is defined by a graphical relationship between the water content, gravimetric or volumetric, and the negative pressure or suction existing in the geomaterial. Such a relationship is termed as water retention characteristic curve, WRCC, or in general water content suction relationship, WSR. In this study, WSR of Indian fly ashes and a pond ash has been developed based on spot measurement. The main objective of the study is to understand the variation in WSR of different fly ashes. Being a cohesionless material, it is presumed that the suction range will be less in fly ash. Therefore, a tensiometer is used for measuring suction in fly ash. Volumetric water content of the compacted samples has been measured using electronic probes. Calibration of these probes is very important for getting correct values of volumetric water content, and hence specific calibration equations has been determined for each of the fly ashes studied. The results were used to determine parameters for WSR, using different WSR fitting functions available in the literature. Based on these parameters and saturated hydraulic conductivity, unsaturated hydraulic conductivity function for different fly ashes has been established. Such functions are required for modeling unsaturated flow through compacted fly ash. Keyword: suction, water retention characteristic curve, gravimetric water content, fly ash, compacted sample, tensiometer, electronic probes, parameter, unsaturated hydraulic conductivity. 1. Introduction. Some projects in geotechnical, hydrological, and environmental engineering are associated with saturated and unsaturated flow through geomaterial. External factors such as rain infiltration cause variations in water content and consequently the pore water pressure, affecting not only the shear strength, but also the hydraulic conductivity. These days fly ash has found wide application in agriculture, landfill liners, and covers, where its water retention characteristics become important. Water retention characteristics are generally defined as a graphical relationship between the water content, gravimetric or volumetric, and the negative pressure or suction existing in the geomaterial. Such a relationship is termed as water retention characteristic curve, WRCC, or in general water content suction relationship, WSR. There are several methods for determining WSR in the laboratory and in the field. 2. Testing methodology. Measurement of suction and establishing water suction relationship, WSR, is important for the study of the unsaturated soil behavior. This WSR relationship is required for determining different unsaturated property function and modeling the behavior of unsaturated geomaterial. With this in view, the deals with an explanation of suction, WSR, and the instruments used in present study for suction measurement. The description of volumetric water content probes, its principle of measurement for fly ash is discussed. 2.1 Measurement of volumetric water content. It is found that volumetric water content is one of the most vital parameter for estimating the suction and in defining the WSR. Hence, needs to be determined very precisely. In view of this, capacitance probe EC5 and ECTE, developed and supplied by Decagon Devices Incorporated, USA, that is capable of measuring, are used in the present study. Details and basic concepts of these instruments are discussed as follows: an AC2OTE, designated as ECTE, and AC2OEC5, designated as EC5, capacitance type probes, as depicted in Fig. 1 and 2, respectively measures based on the dielectric constant or permittivity of the material in which they are inserted. EC5 is two-pronged, whereas ECTE is a three-pronged probe. ECTE measures bulk electrical conductivity and temperature in addition to. The prongs are made of epoxy-impregnated fiberglass, circuit board material. It must be specifically noted that the probe averages over the entire length of the prongs. 3. Working principle. The basic principle behind the working of probe is that the dielectric permittivity, E, of soil medium changes with its water content, as shown in Fig. 3. E is dependent on the capacitance property of the soil mass. The probes measure the capacitance property and give the output in millivolt, MV. The MV output is further converted to, based on the calibration equation, Decagon Devices, USA. The value of E for water is close to 80, dry soil minerals is around 4, and for air it is 1. This means that for highly saturated and dry soil mass, the value of E would vary between 80 and 4. This broad range of E is used to determine of a soil mass. Appropriate calibration equation parameters have been used for geomaterial used in the study by performing laboratory calibration. The probe comprises of an oscillator working at a frequency of 70 MHz, which generates an electromagnetic, M, field. The M field charges the soil around the probe. This stored charge is measured using copper traces provided on the prongs and is proportional to E and. It must be noted that the M field produced by the probe decreases with distance from the probe surface and has little or no sensitivity at the extreme edges of the probe. The stored charge thus measured would confine to a zone of influence of 50 mm measured from the edge of the prong. Measurement of suction. The details of instruments used in the study for suction and volumetric water content measurement are listed in table. T5 tensiometer. T5 tensiometer depicted in Fig 4 has been used to measure .m up to 80 kPa. As shown in the figure, T5 tensiometer essentially consists of three important parts: tensiometer body, shaft, and a ceramic cup. The tensiometer body houses a pressure transducer that is capable of continuously measuring the vacuum pressure or negative pressure created in the shaft during .m measurement. The pressure transducer consists of a plastic body with a thin silicon chip semiconductor that is capable of capturing the vacuum or negative pressure created in the shaft. The tensiometer body is threaded to a transparent acrylic shaft of 100 mm length, which is filled with distilled water free from air bubbles. The other end of the shaft is connected to a tensiometer ceramic cup. This ceramic cup acts as an interface between soil and the shaft and maintains continuity of water through its pores. The ceramic material used has a pore size of 1 m with a homogeneous pore size distribution. Such a pore size distribution is capable of achieving an air entry value of 300 kPa, T5 User Manual, UMS 2001, and therefore provides reliable tensiometric measurements up to suction close to 100 kPa. However, the measurements were restricted up to 80 kPa. Conclusions. Calibration of two different, EC5, ECTE, low-cost probe has been conducted for fly ashes. Spot suction measurement of different fly ash with their mixes, 50:50, with commercially available bentonite has been performed. Estimation of unsaturated permeability function of different fly ashes and mixes has been done by Soil Vision database. 4.23 software using KSAT and WSR. The following conclusions are deduced from this study. The manufacturer calibration equation used by the probes, EC5, ECTE, is not suitable for the fly ashes. New calibrated equation for EC5 and ECTE are more suitable than old calibration equation. Tensiometer measurement of suction is sufficient for fly ashes but it is insufficient for mixes. Parameter obtained by fitting of WSR for fly ashes are nearly equal with reference to the range of suction, 1 to 1 million kPa. Estimation of unsaturated hydraulic conductivity with the help of SWR curve gives proper result and it can be used for seepage modeling. Future scope of the work. Measurement of suction for fly ash need to be performed with higher suction range instrument for obtaining residual suction. Spot measurement suction need to be compared with continuous measurement suction. SWRC results of Indian fly ash and estimated unsaturated permeability functions need to be used for seepage modeling for knowing the effect of fly ashes on seepage modeling. Estimated unsaturated hydraulic conductivity need to be compared with experimental values. Empirical equations and SWRC parameter used for estimation of unsaturated hydraulic conductivity need to understand.